Okay, so let's talk stress analysis. Fun times, eh? So stuff we've covered before, we've been dealing with static equilibrium. We've been dealing with how to find and represent internal loads, so talking in terms of forces. Now we're going to be looking at stress. Stress is basically how concentrated a load is, how the intensity of that load. It's vitally important in basically every design you're ever going to do, because it is typically going to be the limiting factor on whether or not this thing's going to break or not. So you definitely need to have a decent understanding of how to do some stress analysis. So again, we're using it to allow us to basically design our parts so that they're the right size, right material, so on and so forth. Is it going to be strong enough? Is this thing going to actually break when we load it up? Is it going to be rigid enough? I mean, it might not break, but is it going to sag too much? If you have, say, a car that's ends up sagging enough when you get into the seat that the undercarriage starts dragging on the floor, then even if it doesn't break, that's still not working. Does it maintain its geometric integrity? So basically, if you might push it over a little bit, then it might be fine, but if you push it over too much, then you might move past a point where it's stable. So is it going to tip over? Is it going to buckle? Buckling is important too. You'll learn more about that next year. Another thing you'll learn about next year is cyclical stress and how that affects things. So basically, it's a concept we call fatigue. So basically, if you apply a load to something and just increase that load until the breaking point, it's going to break. But if you apply smaller cyclical loads to it, so if you're pulling, pushing, then components have a tendency to break at far lower stress levels than they would if it was just a static load. So that has to deal with cyclical stresses, so repeated stresses over time. So like a piston on an engine, it's going to be experiencing loads as it moves. So it's going to have a certain kind of lifespan to it. And then we got toughness. So that's the other end of the extreme for non-static loads. This is basically if it's hit by something, subjected to an impact or a very fast loading condition. It needs to be able to absorb that energy without causing too much damage. So we talk toughness, we often talk in terms of energy, but that's a bit beyond this lecture. We'll be discussing a bit more about material properties later on. So a few assumptions we're going to be making. So we're assuming that the material in question is homogeneous and continuous. So again, it doesn't have any internal flaws. It doesn't have any cavities. It's all the same stuff. You don't have pockets of copper mixed in with your steel. It's isotropic, so that's saying that the material properties don't vary with your orientation. So that's usually a very good assumption for metal. Some other materials that you might be working with, it's not a good assumption. The one that you're most likely to come up with this being a major issue is composite materials. Composite materials are very anisotropic. They are a lot stronger and stiffer if you pull them in the same direction as the reinforcing fibers are going than if you push or pull them in the opposite direction. Or sorry, in any perpendicular directions. They are known as an unstressed initial state. So basically, we're applying some sort of loads to our structure, and we're assuming that the only forces that get induced are due to those loads. So we don't have some sort of initial state where the parts of the structure are pushing up against one another. And we're working with the assumption that deformations are small. We're working within the linear elastic regime. Again, we'll talk about that in a lecture or two. And we're also able to make the small angle approximation. So it can sometimes help us simplify our math if we assume that when working in radians that the sine of an angle is that angle. Reasonable enough. Anyways, so the general process that we typically follow, so we look at the forces and conditions of equilibrium, and then we kind of look at what sort of displacements will occur based upon those conditions and what our geometric compatibility conditions are. So essentially, like there'll be certain conditions where if you load it up in a certain way, you can tell some things about how different parts of the structure are compatible with one another. For example, if you have a table with 4 legs and you press down on and you apply a load to the surface of the table, your geometric compatibility condition is going to be that the displacement caused by that is going to be equal in all the legs, basically. So they're going to be pushed down a certain amount due to the load, and it's going to be kind of equally shared amongst all the legs. And then we apply our force displacement relationships. Once we figure out the displacements, we can work from there to kind of figure out what our stresses are, or vice versa. So anyways, stress analysis, again, it's a very important tool. It's a tool we use to figure out whether or not our components that we've been designing are safe to use. Whether or not this thing's going to break, whether or not it's going to break catastrophically, or how it might break in the conditions we want. And often, whether or not, usually what we want is we don't want it to be yielding at all. So we don't want any permanent deformation going on. So basically what that means is that if we load it up, if we pull on something, it's going to stretch a little bit. But when we relax, it returns back to its initial shape. So there's been no permanent deformation, so it stays elastic. So definitions. So we are going to be kind of looking at this. I need to resize my thing here. When we take a section cut of a body that has a load on it, it exposes, we can kind of look at that surface and analyze what sort of internal forces we would need in order to maintain equilibrium. So we talked about that in the internal load section. So for mechanics of materials or strength of materials, we're worried about kind of finding how those forces are distributed on the section cuts. So in particular, we're often worried about finding the spots where the forces are most highly concentrated, the spots where we get the most forces acting upon a tiny little spot, and we call that we'll call that stress. Stress is the intensity of this internal force. So we often kind of conceptualize this by kind of taking a cut, taking another cut, taking a bunch of cuts, and giving us, just a tiny, analyzing the stress at a tiny little section. But we'll talk about the two different types of stress that we're worried about. So we're worried about normal stress. So again, same deal with our internal forces. We differentiate between normal and shear stress. In the same way that we differentiate between normal and shear load. So the normal stress, it's just the intensity of the force acting perpendicular to an area. If we have a force over an area, as the size of the area decreases, it becomes less and less. There's 10 newtons acting on this surface. And it becomes more the distribution of the forces in this area follows this function. We're working with the same sign convention as we saw with air and tender forces. Tensile stresses are always positive, compressive stresses are negative. And again, when we get to the strains portion, you'll see why that's the case. So if you have, say, a little cube that you're analyzing, if you try to make it longer, it's a positive stress. So kind of looking at something like this, if we have a body here and we're applying a force on this end, and we say cut it in half, and we're looking at how this force was distributed internally, those forces would kind of be working kind of distributed across this face. So essentially, in order to maintain equilibrium, if you kind of split this up into a whole bunch of little squares and so on and so forth, kind of say each one of these squares would have a little distribution of a distributed load across it. And the intensity of that, the average intensity of that load is going to be equal to the total force divided by the cross-sectional area. And then we got our shear stress. So again, shear stress is, as opposed to our normal stress, which is acting perpendicular to the plane, shear stress acts parallel to the plane that we're working with. Based upon that, it can have two in-plane components to it. If we have a plane here, we can only push away from it in one direction. It's either, there's only one vector that is perpendicular to this plane, but there's an infinite number of vectors that are parallel to this plane. But obviously, we're going to pick two of them. So we're going to pick, one that's going this way and one that's going that way, so that we're kind of keeping in the same direction, So we're keeping in the kind of the same directionality as the coordinate system that we chose. So the shear stress is typically denoted with a tau here. Sometimes you'll see people using sigmas, the lowercase sigmas. Again, it is a stress, so that's not a terrible thing. They'll use different substricts to differentiate it from the normal stress. So normal stress is almost always a sigma, but shear stress can sometimes be denoted with sigma, sometimes with tau. There are some people out there who will use just a capital S for both of them. I don't like that, but typically speaking, I think that tends to pop up more in the material science world than anywhere else, but most engineers will use sigmas and taus. So yeah, shear stress is calculated just, we got a certain amount of force we're applying to one end of the cube, and we're applying, and it's on the face of the cube itself, we got this distributed load here. It's kind of being applied straight onto the face, and the average value of that distributed load is going to be average value of that distributed load is just going to be equal to the total force applied divided by the area. So again, that's this cross section. That's the area of this plane here. Doesn't necessarily need to be, if this is an actual object, it doesn't have any relation to the area here or the area here. You could have a rod like this. You could clamp your rod down here so it holds, and then you could apply a force here. So the average shear stress that would be induced based upon that would just be based upon whatever force you have and the cross-sectional area here. It doesn't have anything to do with this length. So in general, again, we can take our body and we can slice it up, we can slice it up, we can slice it up until we get a tiny little infinitesimal cube. And we can say that since we have this cube, it's going to have the six faces, but we can define the stress state on those faces. Each face of the cube will have three stresses. They'll have one normal stress, and they'll have two shear stresses. All of those acting perpendicular to one another. And that cube represents the stress state at that point. That gives us. We'll talk about this in a little bit, but obviously, if you're taking the equilibrium condition, the equilibrium of this, this cube, the stress here, the normal stress on this end needs to be equal to the normal stress on this end. Otherwise, this thing's accelerating. So if we want to be in equilibrium, then we need to kind of have those balance out. So there's only three distinct normal stresses that you can have, and there are also only there's six distinct shear stresses, but there's only three independent shear stresses, and we'll get into that in a little bit. So units, talking about units in the SI system. Okay, so yeah, stress in general, it's the force intensity over unit area. So in SI, we're working with a Newton per square meter. Those are the base units for force and length. So the unit we use, so we're working with newtons per meter squared, and we have a unit for that. We call that the Pascal, in honor of this guy, who was one of the founders of the field of fluid mechanics. He's the one who invented the hydraulic press and a whole bunch of other things. So one thing to keep in mind is that a single Pascal is very small. So we tend to work with megapascals. So 10 to the 6, which if you're calculating your stresses, works out to 1 Newton per millimeter squared, which is often a quite convenient way to do your calculations. So that's quite helpful. So that's the units we use in SI. In the Imperial system or US Customary. So the base unit of force is the pound, and the base unit of length is the foot. But of course, they're all screwed up, so they don't use both of those to define the pressure. Instead, they use inches. So the units that is used is pounds per square inch. So PSI is a pound per square inch. Again, relatively small compared to what we tend to see in solid mechanics. So they tend to use kilopounds per square inch KSIs. And if you want to convert from system to system, 1 KSI is 6.89 megapascals. So notation-wise, like I said, we use subscripts to differentiate kind of which stress is which. So if you have a again, like I said, some people use all sigmas here. So you may not have the tau as an indicator that it is a shear stress. But if you have the same subscript for both, if you have the same direction from both subscripts, then that's a normal force. Whereas if you have a different subscript for the two different subscripts, then that's a shear stress. If, as shown here, you're only given one subscript, then that's implying it's a normal force. Essentially saying, instead of saying sigma z, they just said sigma z, and you could figure out that because they only gave you the one, that it is a normal force. So the way those subscripts works is that you have the first one defining the face that the stress is acting upon. So if we're trying to find sigma xx, sigma the first one here defines the face it's acting upon. So the face that is kind of pointed towards the x direction. In that instance, the vector perpendicular to this force is in the x direction. So this here is the x face, this here is the z face, and this here is the y face. And again, that's obviously completely based upon the coordinate system chosen with x here, y here, and z here. So that's the first subscript, and then the second subscript tells you what direction that force is pointed. So if you're acting on the x face and you're pointed in the x direction, then that's a normal force. Whereas if we have this one here, we're acting on this face, we're acting on the x face, but it's pointed in the y direction. So that's a shear force, because the directionality of the force is parallel to the plane of the face. And then this one here, acting upon the x, pointed towards the z, like that. So similarly, like tau z, zy, that's acting upon the z face and pointed towards y, like that. So sign conventions, again, tensile is positive, so your force arrows are pointed away from the plane. The forces that are acting upon there are stretching out this section of the object. Compressive is negative, so the arrows are pointed inwards. And again, you can have situations where you have a positive normal stress in one direction and a negative normal stress in another direction. That happens all the time. As for shear stress is a bit more annoying when it comes to sign convention. So again, it's absolutely based upon the coordinate system chosen. So again, you're picking the front face for the shear. So that's basically, that'd be this face and not this face. The one that's you want to pick the face that is kind of where the normal vector of that from that face is pointed in the direction of the positive direction for the coordinate system chosen. So again, in this coordinate system, this is the positive y, this is the positive x. So this is the front face for the x. This is the front face for the y, because a normal from this is pointed in the same direction as the positive of the positive direction of that axis. So once we define the front face, basically a shear is positive if it is acting on the front face and pointed in the same direction and pointed in a positive direction. So this one's acting on the front face and it's pointed up. When up here is defined as positive in the y direction, then that's positive. So this one here, based upon the fact it is acting on this shear force right here, that one is a tau x because it's acting on the x face, y, because it's acting on the x face and it's pointed in the y direction. So and it's pointed in the positive y direction. So it's a positive tau xy shear. And then here we got the opposite. We've got the front face, but the force is acting downwards relative to the direction of y. Or, alternatively, you've got a positive y force, but it's acting on the back face. Either way works. It's, you're multiplying it by -1 one way or the other, either the directionality or the wrong face. It's generally the least confusing if you always work on the front face. Don't try to avoid looking at what the back face is doing if you can. And the annoying part is, so the sign conventions for a right-hand coordinate system, again, I would like to emphasize that you do not have a good reason to be using a left-hand coordinate system. There may be some other fields of study where people could convince you to use a left-hand coordinate system. Engineering's not one of them. It's like learning about masculine and feminine verbs in French, and then showing up and deciding to use them in English. Masculine and feminine nouns in French, and then showing up and deciding that this cup needs to have some sort of masculinity or femininity to it. You're speaking a different language, and you really shouldn't be. So don't use left-hand coordinate system. The problem is that rotating your coordinate system by 90 degrees, which you're totally allowed to do, as long as you're consistent, both of these are perfectly valid coordinate systems. Unfortunately, they will cause the same set of shear to change sign. So you need to keep your coordinate system consistent when you're analyzing shear. Otherwise, you will fuck things up. So as an example, let's look at what the stress tensor is for this particular stress state shown. So I'm going to draw this. So again, we've got the components here. So let's see. Let's start with our x, our normal x. So we got the x face here, and we've got the force that's acting in the x direction. That one's going to be 10. That's a positive 10 because it's pulling. Let's our y face. So we got the y face here, and the direction that's acting parallel to the y, that's 20. That's a -20 because it's pushing inwards towards the cube instead of pulling away from the cube. So -20. And then z, again, Z face here in the Z direction, that'll be 10. So we got that. Let's fill in the others. So our tau xy is the next one here. So our tau xy is acting on the x face, and it's pointed in, acting on this face, and it's pointed in the direction of y. So again, we are looking at our front face here. This cube here is only showing the front faces. So it is this would be a positive shear force if it was acting in this direction. Unfortunately, well, not unfortunately, it isn't. That's not unfortunate or not. It just is or isn't. So that one is going to be a -5. And then the next one here is our tau xz. So that'll just, x direction, x face, z direction, +2. And then we can fill in the rest. Okay, so we've got this force here, this shear stress here, that 5. Again, positive y. It's on the front y face. It's pointed away from the positive x direction, so that's a -5. That having been said, I'll talk about this in a second. These values need to be the same. This needs to be the same. These two need to be the same, and this one need to be the same. So I'm just going to fill that in there, because again, this matches that. This matches that. So the only one we're missing is our tau zy's. Or our tau yz, whichever one we want to find first. So so we got our tau z face, y direction. So that's -15 because that one's on our front z face, but pointed away from the positive y direction. So -15 there. And again, like I said, those need to be equal. So that, and we'll talk about that in a second. That's what we get for filling in our stress tensor there. So, before we get to that shear that shear condition, that shear matching condition that I talked about, talk about average normal stress. So essentially, if we take a bar and load it through the centroid of its cross-sectional area, it's going to deform uniformly. Again, assuming it's homogeneous and isotropic. I don't know why this dropped the I on isotropic. I think I hit enter in the wrong spot anyways. Isotropic. So when we zoom in and look at this, we get these tiny little cross-section areas, and each of those is going to be having a little force applied, and that force is going to be, that little bit of force is going to be equal to the stress state there times the little bit of area that we're looking at. So if we take that and integrate over the area, we get the total load. So essentially what we're saying is that we can calculate the average stress by finding our P, just taking our total load and dividing by the cross-sectional area. So if we're looking graphically, we can find, if we have this cross-sectional area here, and we've got this stress function going on here. So the stress, if we got this distributed stress load, and that is going to be a function of the position, on the face in X or Y, then we can find the the magnitude of that resultant is going to be found by the total volume under that stress diagram. And then the same deal as we saw when we looked at our distributed loads previously. That resultant force passes through the centroid of that volume. That having been said, we tend not to deal with this graphically too much. There's little tricks to try to figure out how these stresses kind of how to find how to find a decent resultant for the stresses, but we'll get into those. So again, just again to emphasize, the average normal stress is based upon the load divided by the area, and we're still going to be using the convention that the internal load needs to be defined as positive when it's a stretching or negative when it's a compression. So again, in this situation, that P there should be negative, which gives us a negative stress value that we solve for this. So and again, it is a function of your load, and it's definitely a function of the area as well. So again, we got this tiny little rod here, 1 millimeter rod, really more of a wire at that point than a rod. Sorry, a 1 millimeter squared cross-sectional area, so a relatively thin wire. Or we've got this other rather more honking one that has a cross-sectional area of 100 millimeters squared. So again, that would imply that this thing has a diameter that's 10 times this one. So again, due to the fact that the area is larger, despite the fact that this load is larger, the stress state, the stress that's going to be induced is going to be smaller here than it is here, because stress is all about the force intensity. So trying to carry it over a smaller area is going to lead to higher stresses, which is going to lead to failure fast. And I don't think anyone should be too surprised at that. The concept that big, thick rods can carry more of a load than small, skinny wires is relatively intuitive to almost everyone. Next, we got our shear stress. So again, it's acting in the plane of the sectioned area. So if we look at kind of a setup like this, or we got this bar sitting on two other bars, and we're applying a load kind of in the center. If we take some cross-sectional cuts and do a little bit of force analysis, equilibrium analysis here, so we're gonna have the force there, and it needs to have an internal load such that on either side of that, it's got an internal shear whose magnitude, again, in this loading situation, is going to need to be F divided by 2. So again, we'll note the switch of the sign. This was loaded downwards, the V's upwards, and again, that's because V there is a reaction to the applied load. So if we the shear that we're looking at is basically just this shear load distributed across this area. So if we're looking at the average shear, if we're assuming that it's evenly distributed across that area, which, spoiler alert, it's not, but you don't need to worry about that till next year. If we assume that the average shear is evenly distributed, then it's just going to be equal to that V over A. So for this particular loading situation, that'll be F over 2A. So, as an example, if we have two plates and we're trying to pull those plates apart, but we can't because there's a bolt that we connected those two plates with, then essentially what we're going to need to do is draw a little diagram here. So we've got a bolt going through there. I hate it when I think I'm trying to move stuff instead of drawing more lines. So essentially, if we just look at the force, so we got this P here, I got this P here. So each of those plates is going to apply to the bolt. Looking at just the bolt here. Going to apply a P, and it's going to apply a P. So if we take a section cut right here, let's look at the other side so I don't have to draw the head of the bolt. We take a section cut here, got this P down here, and in order to resist that, in order to maintain equilibrium, it's going to need to have a shear load, V, and that in this instance, in this loading condition, that shear needs to be equal to P. Again, different than this loading situation. That would be like P over 2. That's because this thing's supported on both sides. So the shear load here is just our V is equal to P, so therefore our tau is always our V over A, which in this instance works out to P divided by pi times the diameter squared, all divided by 4, because we're working with diameters, not radiuses. Had a few people who, oh, sorry, I realize you can't see that underneath my face there. That shouldn't have been that high. Oh, I see what I did. Yeah, anyways, sorry. So yeah, that is that. So, and I just move the 4 over to the top, I guess, for P over pi times 25 by 25 is 625 millimeters squared. That's good enough. So again, and the direction, the orientation of that will depend upon what sort of coordinate system we chose. So let's go ahead and just define that here now. Let's make this x. Let's make this y. So in this instance, this face here, that face there is going to be that's going to be the back face of the x directionality, and the force is acting in the positive y direction. So it's going to be a tau xy, and it's actually going to be negative, kind of just based upon that coordinate system chosen. Okay. So another example, so if we want to figure out the average shear stress in the 20 millimeter diameter pin that we have here at A. So again, we've been dealing with pinned connections for our equilibrium conditions quite a lot. But we haven't been worried about what's happening at the pin. We've been worried about what the pin does to other stuff, but we haven't been worried about the actual strength of the pin that's carrying that load. So this time we are. So we're worried about this 20 millimeter pin here and this 30 millimeter pin here. So let's go have a look at that. So taking this and placing that setup here with our free body diagram. Again, got our load here, got our reaction for the tension, we've got our reaction at the pin in both y and x. Coordinate system drawn on, dimensions drawn on. So the first thing I'm going to want to do here is I'm going to want to find AY. So I'm going to do that by taking a moment about B. B is this point here. Again, that needs to be equal to 0 for an equilibrium. So just adding those up, AX passes through, the line of action of AX passes through B, so we're not worried about that one. So I got this AY, that's going to be causing a clockwise rotation about B. So negative AY times its 6 meters. And then we've got this 30 kilonewton load here. That's causing a counterclockwise rotation when taken about B. So that one is positive. So then we get to solve 30 kilonewtons times the 4 meters. And we can solve for AY as 20 kilonewtons. Then we can take the sum of our forces in the x direction in order to find what our TBC here is. So we got the plus 20 kilonewtons, we got the minus 30 kilonewtons, and we've got whatever the vertical component of TBC here is. So that'll be 4 over fifths TBC, because again, this is a 3, 4, 5 triangle with the 4 on the vertical component there. So we can solve for TBC as 12.5 kilonewtons. And then we can just take the sum of the forces in x direction to find our AX here. So sum of those forces is equal to 0, so it's minus AX. I drew AX in the negative direction initially because I kind of knew that it would need to be counterbalanced by this. It would need to counterbalance the tension from here. So negative AX plus our tension in BC times its unit vector in the x direction, 3 over 5. That gives us an AX of 7.5 kilonewtons. So that's our static analysis here. So if we want to find how that's affecting the shear at the pins, what we're going to do is for the pin at A, we're going to basically have to find the resultant of those forces acting at A. So the magnitude of that is just going to be based, the square root of 20 kilonewtons squared plus 7.5 kilonewtons squared. So the magnitude of that is 21.36 kilonewtons. So kind of if we're looking at it from the side view here, the beam would be acting upon the pin with a force like that. So if we kind of looked at it at a particular angle, we could just replace the setup like this. So if we look at a free body diagram of our pin, we got the maximum load here of the 21.36 kilonewtons, and then the resultants from the supports here. It's going to be evenly split because it's a symmetrical loading situation. If you don't believe me, you can go ahead and start taking moments and adding forces together. But it'll work out to be half of that. So based upon that, if we take a section at one of these points, we know that the shear load across one of those sections is going to be equal to that half load there. So our average shear, when taken across one of those sections, is just going to be the 10.36 kilonewtons divided by pi times 10 millimeters squared. Again, 10 millimeters squared because it was the pins had a diameter of 20 millimeters. So work it off the radius formula there, not the diameter formula. So again, that once you punch everything in, that ends up being 32.98 megapascals. So the way I get to the megapascals is, this number divided by these numbers gives us 0.3298. But the units there is kilonewtons per millimeter squared. So we take those the newtons per meter squared. We know that that's an MPa. A kilo MPa just means that we need, in order to get to MPa, we need to take that number and multiply it by 1,000. So multiplying that number by 1,000 gives us our 32.98 megapascals. So we're at the right type of unit, and we're at a reasonable magnitude. Then at the other end, again, we've got another loading situation. It's a different one, so it's similar to the one we saw with those two plates that were being pulled apart. So it's a single shear connection. Because you don't have the double supports on either side, you've got the entire shear being carried across this section taken in the middle here. So if you have a situation like this, then the load gets shared on either side. If you have a situation like this, then when you take a section right here, the entire thing is carried by there. So our load's going to be the 12.5 kilonewtons that we solved for as the tension. Our TBC right here, 12.5 kilonewtons. And again, it's working at a particular angle. We don't necessarily need to know what angle it is to figure out what the stress level is in the bolt. We just need to know what it is in order to find that out. So we got the load. So just that load divided by the area. So the area is based upon its diameter. The given diameter was 30 millimeters. Got this load divided by pi times 15 millimeters squared, the radius squared, and that'll give us 17.68 megapascals. Again, using the same conversion formula that we had up here. And that is about that. So next, let's talk about this concept of complementary shear stresses. So this is what I mentioned before about how you really only have 3 independent shear stresses, despite the fact that kind of each face has 2 shear stresses. You might look at that and say, all right, well, if each face has 2 shear stresses, then there's 6 faces, so that's a possibility of 12 different shear stresses. Doesn't quite work out that way. So if we look at this one, at this cube here, let's think about it in terms of equilibrium. So if we were to try to take this cube and apply a shear force to the top of it, what would happen if that's the only force that is acting on that little cube? Well, that thing would shoot off and accelerate in that direction. That's not what we want. So we know that the sum of the forces in the let's see, what is the directionality here? Right, so that's y. This is x, and this is z. So the sum of the forces in the y direction needs to be 0. So if we want to counteract that, we need to apply another force that's going to kind of hold it in place. So the way that's going to happen is it's actually going to get an equal and opposite shear force applied on this bottom face. And that looks a bit like a tau. There we go. So equal and opposite. But we're still not in equilibrium here, are we? Because, all right, we've got the sum of the forces in the y direction balanced out, but now we got a moment couple, right? So if we just left that as is, this thing would just start spinning and spinning and spinning, and that's obviously not actually happening. So what we need to do is we need to have some sort of reaction that occurs in order to cause this thing in order to counteract that moment. So the way that happens is we develop on these faces an equal and opposite shear stress that counteracts that moment. So again, this value here, the value of this stress here, is the same as the value of this stress here, which is the same as the value of this stress here, which is the same as the value of this stress here. So all the forces balance out, the x and the y and the z all balance out, and the moments balance out too. So you get complete so now this thing is actually in equilibrium. Whereas if it wouldn't be if something else, it wouldn't be if there was some other loading condition. So when we get back to this, essentially what we're saying is that if there is any force on this face, so if we take a section of our if we take a section of our object and it's got some sort of shear stress on the plane of that section, we can figure out what that would be, but we also know that it's going to cause stresses kind of at other points around there. So and so that basically means that we narrow it down to, instead of having the 12 different stresses that we might have been able to encounter, the tau zy, that's this one, needs to be equal to the tau prime yz. So that's just the prime here is indicating it's on the back face instead of the front face. So that's equal to that. And it's also equal to the tau yz, and it's equal to the tau prime yz. So all those things are equal. So basically that means that we're down to only 3 independent shear stresses that can arise. You've got your tau xy, you got your tau xz, and you've got your tau yz. So I'm going to draw those ones here. So tau xy, that's right here. You got your tau xz, that's here, and you got your tau yz. So that's this one here. So those are the only 3 independent shear stresses that can occur, because if we have tau xy, then that's going to cause a tau z. Sorry, not xy. If we have a tau xy, that's this one here. That's going to cause a tau yx equal and opposite. If we have our tau xz, that's this one here, that's going to cause a tau zx. And when we have our tau yz, this one here, it causes a tau zy. So these are the only 3 independent shear stresses that can occur. All the rest are a reaction by those shear stresses, or vice versa. So finding the shear stress on, if you find the shear stress on one face, that defines kind of the shear stress on a loop around here. So if you find the shear stress on 2 faces, as long as those faces aren't opposite from on the opposite side of the cube from one another, then you've found all the shear stresses that are happening in that object or in that cube. So that's that's why you have complementary shear stresses. That's why when we go back to our stress tensor, that's why this matches this. This matches this. This matches this. These values are the same. These values are the same, and these values are the same. All right, and that's an intro to stress.